Hello everyone, this is Dr. C.H. Srinivasarao, working as professor in the Department of Electronics and Communication Engineering, Vardhaman College of Engineering. Welcome to my second video lecture on a subject electronic circuit analysis. Today, in this lecture, I am going to explain about the analysis of various multistage amplifiers. How to analyze a multistage amplifier. How to analyze the performance of a multistage amplifier. Then, based on the results we get after the analysis, how to conclude their applications in real time applications, in real time scenario. Right? So, for that, before we directly consider a particular topic, first of all, let me classify the multistage amplifiers into uh, different categories. Depends upon the configurations we use for cascading. Multi-stage amplifiers are classified into number one CE or two-stage RC coupled amplifier. Number two, CE cascade amplifier. Number three, CE cascode amplifier. And number four, CC cascade amplifier or Darlington pair amplifier. These are the various possible multi-stage amplifiers, depends upon the configurations of BJT which we cascade. The most popular cascade amplifier is CE or two-stage RC coupled amplifier. Second one, we can have another combination of CE cascade amplifier. Then we can cascade CE. Of course, this cascade combination of CE amplifier is popular as cascode amplifier. Then finally, we can have CC or Darlington pair amplifier. So, in your university examination point of view or semester end examination point of view, analysis of any of these four amplifiers is a question for you. The question can be like this: draw the circuit of high input resistance amplifier using Darlington pair configuration. With necessary equations, explain how the amplifier can be used as voltage buffer in practical applications. This is, of course, based on the Darlington pair amplifier. This question is based on the last configuration which I have listed here. Similarly, the questions expected based on the CECC and CECB also. Similar type of questions are expected based on the first three configurations also. Good news is the procedure of analyzing all these four amplifiers is exactly the same. That's why I am considering CCCC Darlington pair amplifier as a reference here for the analysis. And if you try to, first of all, try to understand the procedure which I am following, and then follow the same procedure to analyze CECE, CECC and CECB also. Yeah, of course, as we have discussed in the previous lecture, a multi-stage amplifier is a cascaded version of n number of single stage amplifiers. In other words, if two or more than two single stage amplifiers are cascaded or connected in series, such a circuit is called as multi-stage amplifier. I said multi-stage amplifier is having high gain. Basically, multi-stage amplifiers are high gain amplifiers. High gain is meant for amplifying very weak signals. So basically, multi-stage amplifiers are capable of amplifying or improving the strength of very weak signals. That's why in our real-time applications, as we know, the natural source signals are arriving from far away distances from our circuits. Therefore, the strength of natural source signals is very weak. Amplification against those very weak signals is a mandatory requirement in practical applications. Therefore, high gain amplifiers like multi-stage amplifiers are very much required in real-time applications. That's why design and analysis of various multi-stage amplifiers is the topic for us in today's class. Now, let's go for one of the circuit analysis. This is the question, of course, I repeat. Draw the circuit of high input resistance amplifier using Darlington pair configuration. With necessary equations, explain how this amplifier can be used as voltage buffer in practical applications. So first of all, let us, of course, for this question, you have to start with the basic circuit. Not only Darlington pair, even if the question is based on CEC or CECC or CCCC, CECB also, first of all, you have to draw the basic circuit like this. Transistor version, you have to draw the circuit which is popularly called as basic circuit. So the basic circuit of a Darlington pair amplifier is shown here. Look at this. Input signal is applied at the base of transistor 1. Input signal is applied at the base of transistor 1 and output is obtained at the emitter of transistor 1. That's why first stage is a CC configuration. Of course, collector is common for both input output sections here. Therefore, the first stage is Q1 is operated in common collector configuration. Similarly, if you look at the second stage, input is applied at the base and output is obtained at the emitter. So that means Q2 also operated in common collector configuration. So as a result, these two transistors Q1 and Q2 are operated in CC configuration, and this configuration is very familiar with the name Darlington pair configuration or Darlington pair amplifier. Then in the analysis of any multi-stage amplifier, after drawing the first basic circuit as first level, at the first level, then you have to draw the small signal model of the circuit. Small signal model, of course, in the subject called electronic devices and circuits, which you have studied in first year, you might have already obtained, you might have already seen this H parameter model analysis, H parameter model or small signal model for BJT. The same H parameter model or small signal model I am using here for both the transistors Q1 and Q2. Q1 is replaced with H parameter model and Q2 is also replaced with H parameter model. Just carefully observe the H parameter models I have used here. Between B1 and collector 1, HIC, because the first transistor is operated in common collector mode. Therefore, B1, between B1 and C1, HIC and HRC VE1 is the equivalent circuit at input side. Then coming to output side, between emitter and collector, one current source HFC IB1 and 1 by HOC is the output admittance. These are the two components we represent at the output side. And the same diagram is repeated for second transistor also, because second transistor is also operated in common collector configuration. Then with the help of small signal model, we have to analyze the amplifier circuits in step by step. Remember, when you are about to analyze a multi-stage amplifier, please keep these clues or hints in mind. You have to complete the analysis in 3 different levels in a multi-stage amplifier or 2-stage amplifier otherwise. First of all, you start with the second stage or the last stage. The stage which is connected to load is to be considered for analysis. Complete the analysis for 4 different reference parameters, namely voltage gain, current gain, input resistance, output resistance of the second stage. Then consider the first stage analysis again. Again complete the analysis for voltage gain, current gain, input resistance and output resistance of the first stage. Then by clubbing the first and second stages, overall analysis you are supposed to consider. Means overall voltage gain of the total amplifier, overall current gain, overall input resistance and overall output resistance. Based on the results you get for those overall parameters, you have to conclude in which particular area of application this circuit is suited in real time scenario. That's what the total procedure which you are supposed to follow in every multi-stage amplifier, not only in the circuit, even in the remaining multi-stage amplifiers also the same procedure you need to follow. I just repeat the procedure. The procedure is: first you analyze second stage for four reference parameters, namely voltage gain, current gain, input resistance, output resistance. Then consider the first stage. Again complete the analysis for those four reference parameters. After getting the equations for voltage gain, current gain, input resistance, output resistance of the first and second stages, then go for overall analysis. Obtain equations for overall voltage gain, overall current gain, overall input resistance and overall output resistance. Based on the results of those overall parameters, we can have a summary statements. Yeah. Now let's consider the analysis of this Darlington pair amplifier. As I said, first consider the second stage. That too, in every amplifier's analysis, first you have to estimate load resistance. Unless you estimate load resistance, you cannot estimate any of the parameter. That's why first start with load resistance in this case. Step 1, load resistance RL2, second stage. Because I am analyzing second stage, I am using a suffix 2 for all the parameters. The suffix 2 indicates second stage parameters. RL2, if you just look at the circuit again, what is the output resistance or load resistance of the second stage? If you look at the circuit here, load resistance of the second stage is nothing but RE. This is the load resistance. So RE itself is the load resistance of the second stage. Then once you estimate load resistance in an amplifier circuit, you are in a position to estimate current gain in that amplifier. Once you estimate load resistance in any amplifier circuit, you are in a position to estimate current gain. So current gain of second stage. What is the general formula for current gain in any amplifier? Output current by input current. So I naught by II is the formula. As you are talking about second stage, you write it as I naught 2 by II2. Then if you go back to the circuit arrangement, what is I naught 2? I naught 2 means output current into the load, which is nothing but minus IE2. Minus IE2 is the output current and IB2 is the input current. So rewrite the equation like this. This is minus IE2 by IB2. That means we have to obtain an equation for this minus IE2 by IB2. But in a common collector configuration of BJT, there is a reference equation for IE2 or output current. Of course, from the basics of BJT, to obtain small signal model or H parameter model, you might have used a general equation called output current is a function of input current and output voltage. In other words, I2 equal to H21 I1 plus H22 V2. That's what the equation you might have written. With respect to common collector, the same equation can be written as IE2 equal to HFC IB2 plus HOC VE2. This is the equation available with us. Then if you go back to the amplifier circuit, here at the output section of the amplifier, look at the output section of the amplifier here. We can write VE2 equal to minus IE2 into RE. VE2 is nothing but voltage across RE. Current into RE is minus IE2. So minus IE2 into RE is VE2. So substitute that value of IE2, sorry, VE2 in this equation. So this is HFC into IB2 minus HOC into IE2 RE or RL1, RL2, sorry. RE is nothing but RL2. You can also write this RE as RL2. Then bringing this HOC IE2 RL2 to left hand side and taking IE2 common, you will get it as IE2 into 1 plus HOCRL2 equal to HFC into IB2. From this, IE2 by IB2 equal to HFC by 1 plus HOCRL or RL2. Then if you go back to equation 2, what is the parameter actually we are trying to estimate? We are trying to estimate current gain. Current gain is actually given by minus IE2 by IB2. But as of now, we got an equation for IE2 by IB2, which is HFC by 1 plus HOCRL2. Therefore, let's write an equation for AI2. AI2 equal to minus IE2 by IB2 equal to minus HFC by 1 plus HOC RL2. This is the equation for current gain we got. You have to understand this analysis carefully. Why? Because the same procedure or the same analysis we have to do for first stage also. Because first stage is also a common collector amplifier. Whatever the procedure I have followed, the same procedure is to be useful for the first stage also. You try to understand this analysis. Then, after estimating current gain, we are in a position to estimate input resistance of the amplifier. Step 3, the formula for input resistance in any amplifier is Vi by Ii. As we are analyzing second stage of the amplifier here, I will use a suffix Ri2 for this. So, I will write it as Vi2 by Ii2. In common collector amplifier, Vi2 means Vb2, Ii2 means Ib2. For this, we need to obtain an equation. We have to obtain an equation for this. And again, of course, from the basics of BJT or from the small signal model which you have studied in first year, we have a general equation for input voltage. Input voltage is a function of input current and output voltage. Based on that, we can write an equation for VB2. Consider the equation for VB2 we have VB2 equal to HIC IB2 plus HRC VE2. This is the equation available with us. Then what you do is you divide this equation with IB2. Divide this equation with IB2, which will give us VB2 by IB2 equal to, of course, nothing but input resistance Ri2 equal to HIC plus HRC. Just before this step, while estimating current gain, we got an equation for VE2 as minus IE2 RE or RL2. Minus IE2 RL2 was the equation we got for VE2 by IB2. Then you can rewrite this equation for input resistance Ri2 as HIC plus HRC. This minus IE2 by IB2 minus IE2 by IB2 is nothing but current gain. So, HRC into AI2 into RL2. This is the equation for input resistance. This is the equation for input resistance. Again the same story. You need to understand this analysis. Why? Because the same analysis we are going to use in case of first stage, because first stage is also a common collector amplifier. Then once after estimating input resistance and current gain, already in first step we have estimated current gain. In second step we have estimated the input resistance now. Then with the help of these two parameters, we are in a position to estimate voltage gain. Step 4 is voltage gain, that is AV. Of course, the general formula for voltage gain in any amplifier is V0 by Vi. Of course, we are talking about second stage here. Instead of AV, I am calling it as AV2, and the output voltage I am calling it as V02, and the input voltage I am calling it as Vi2. That is, AV2 equal to V02 is nothing but minus IE2 RL2. V02 is nothing but VE2, that is minus IE2 RL2 by VI2 is nothing but IB2 into RI2. IB2 into RI2 is AV2. But minus IE2 by IB2 is nothing but current gain. So this is AI2 into RL2 by RI2. This is the formula for voltage gain. This is the formula for voltage gain. We can approximate this voltage gain to from this input resistance. We can go for some simplification. That simplification will help us to approximate this voltage gain. Look at the input resistance here. Equation for input resistance, if you carefully observe, we know from the typical values of H parameters, HRC is 1. HRC is 1, right? Therefore, if HRC is 1, this equation can be approximated to HIC plus AI 2 RL2. Because HRC is 1, this equation 5 can be approximated to HIC plus AI2 RL2. Then from this AI2 RL2 equal to RI2 minus HIC. AI2 RL2 can be equal to RI2 minus HIC. Then if you substitute this value of AI2 RI2 in this equation, you will get AV2 as approximated equation as AI2 RL2. We can replace this numerator with RI2 minus HIC. RI2 minus HIC by RI2. What it will be? RI2 gets cancelled, and this can be approximated to 1 minus HIC by RI2. 1 minus HIC by RI2. Keep it as the final equation. We will be using this value of AV2 in our further discussions also. Therefore, AV2 can be approximated with this equation. Output resistance. Step 5. Output resistance. Output resistance R02 we are supposed to estimate, means V02 by I02 is the formula. Even though output resistance is the parameter we are supposed to estimate V02 by I02, but it's quite natural practice to estimate output admittance in amplifier circuits. That means rather than estimating output resistance, I am going to estimate output admittance, that is Y02. Y02 equal to I02 by, in fact, the output current IE2 by VE2. This is what the parameter I am going to estimate. While estimating output resistance, there are two very important conditions you are supposed to implement. That's what you might have already observed in the subject called EDC also. While estimating output resistance, two conditions are with, in fact, V02 by I02 with load open and Vs are input voltage 0. These are the conditions we are supposed to follow for the estimation of output resistance. There are two very important conditions we are supposed to follow. The two important conditions are load is open and source voltage or input voltage 0. So why not 2 at present, instead of estimating output resistance, you will come to know, for mathematical convenience only, instead of going for output resistance, it's quite natural practice to estimate output admittance in amplifiers, which you have already done. It's not a new thing for us. I am not doing it for the first time. You have done it in the EDC also. So while estimating output admittance, the formula is IE2 by VE2. This is, of course, we have a formula for IE2 as HFC IB2 plus HOC VE2 by VE2. So from this, I am going to write the first term Y02 equal to HOC plus HFC into IB2 by VE2. This is the equation we get up to this level. Just keep it as one equation. Then we have to simplify for this IB2 by VE2. For this, consider the formula for VB2. VB2 equal to HIC IB2 plus HRC VE2. This is the equation available with us, general equation. But according to the second condition, Vs or Vi should be equal to 0. Input voltage must be equal to 0 for the estimation of output resistance. That means this must be equal to 0. From this, we can get an equation for IB2 by VE2 equal to minus HRC by HIC. Then if you substitute this value of IB2 by VE2 in equation 1, you will be getting the output admittance as equation 2 in equation 1 will give us Y02 equal to HOC minus HFC HRC by HIC. Of course, our task is estimation of output resistance R02 equal to 1 by Y02. This is the complete analysis of second stage of the Darlington pair amplifier. Remember, Darlington pair amplifier contains two stages. Both are CC amplifiers only. As of now, we have completed the analysis of second stage. Good news is, analysis of first stage is exactly the same because first stage is also a CC amplifier. So that's why instead of going for the analysis again, what I am going to do is, I will just list out all the final equations for voltage gain, current gain, input resistance and output. Case 2, first stage. Of course, first stage is also a CC amplifier. Yeah, step 1, load resistance. Load resistance of first stage is equal to input resistance of second stage. Then current gain of first stage equal to minus HFC by 1 plus HOC RL1. Of course, this is minus IE1 by IB1. Directly I wrote this equation because already we got this equation in case of second stage. Second stage is a CC amplifier. First stage is also a CC amplifier. So both are exactly the same. So that's why instead of going for analysis separately, I wrote this equation for current gain directly. Next parameter is input resistance. Input resistance formula for first stage RI1 equal to HIC plus HRC AI1 RL1. However, as I told you earlier also, this HRC equal to 1, we can replace this HRC with 1 and can be approximate this equation to HIC plus AI1 RL1, which we will be using in our further levels. Then next parameter is voltage gain of first stage. This is AI1 RL1 by RI1, which can be approximated to 1 minus HIC by RI1. Finally, output resistance or output admittance of first stage is HOC minus HFC HRC by HIC, and output resistance in case of first stage is 1 by Y01. So far, we have analyzed the second stage and first stage in Darlington pair amplifier. Now it's time for us to go for overall analysis. For that, whatever the analysis we have made so far is to be used for the estimation of total overall voltage gain, overall current gain, overall input resistance and overall output resistance. Let's do that now. First, let us start with overall voltage gain, AV. Of course, in Darlington pair amplifier, overall voltage gain in any amplifier is output voltage by input voltage, V0 by Vi. But however, if you look into the circuit there carefully, overall output voltage is nothing but emitter voltage of second transistor, whereas input voltage is nothing but base voltage of first transistor. So we can write this as VE2 by VB1. But if you look into the analysis we have completed in case of second stage and first stage, we don't have any formula for VE2 by VB1. That's why for time being, I will rewrite this equation as VE2, I will divide and multiply this equation with VB2. So VE2 by VB2 into VB2 by VB1. Just for mathematical convenience, I wrote like this. But we know VB2, VE2 by VB2, base voltage of second transistor is VB2. Output voltage of second transistor is VE2. So VE2 by VB2 is nothing but AB2. At the same time, if you carefully observe, the output voltage of first transistor is emitter voltage, VE1, and is simply equal to base voltage of second transistor, VB2. That means from this circuit, we can say that emitter voltage of first transistor and base voltage of second transistor both are at the same level. As a result, we can rewrite this VB2 as VE1 by VB1. Then what is VE1 by VB1? VE1 by VB1 is nothing but voltage gain of first stage. That means we can write it as AV1. So this is AV2 into AV1. This is the overall voltage gain in case of Darlington pair amplifier. Already we got equations for AV2 and AV1. Let us substitute those equations here. We got AV2 as 1 minus HIC by RI2. Similarly, voltage gain of first stage is 1 minus HIC by RI1. These are the values of AV2 and AV1 respectively we got in the analysis, previous analysis we have made in case 1 and case 2. We know RI2 is always much greater than HIC. So we can approximate these values. First value 1 minus HIC by RI2 can be approximated to 1 into this 1 minus HIC by RI1 is also approximated to 1, because since RI2 is much greater than HIC and RI1 is also much greater than HIC. Then what will be the overall voltage gain of Darlington pair amplifier? 1. So from this equation, we can conclude that Darlington pair amplifier is a unity gain amplifier. This is the first conclusion. Unity gain amplifier. Since the overall voltage gain is found to be approximately equal to 1 in Darlington pair amplifier, it is popular as unity gain amplifier. Step 2, overall current gain, that is AI. Of course, in any amplifier, overall current gain is equal to I0 by II. But if you look at Darlington pair amplifier which we have drawn in the previous slide, overall output current is nothing but minus IE2. Overall input current is nothing but IB1. So we can write the I0 value as minus IE2 and II value as IB1. Minus IE2 by IB1 is the equation for overall current gain. But unfortunately, we don't have direct formula for minus IE2 by IB1. That's why what we do is, let us rewrite this equation like this. This is, you keep minus IE2 as it is, and then divide and multiply this equation with IB2 into IB2 by IB1. Then simply what we can say, minus IE2 by IB2 is AI2 into, then if you look at the circuit again, IB2 is nothing but base current of second transistor is nothing but emitter current of first transistor. Just carefully observe that, because both emitter of Q1 and base of Q2 are at the same node. So emitter current of first transistor IE1 and base current of second transistor IB2 should be equal. If that is the case, we can simply replace this IB2 with IE1 by IB1. What is this IE1 by IB1? Of course, IE1 by IB1 is nothing but current gain of first transistor. So this is AI2 into AI1, where AI2 in the analysis, case 1 analysis, we got it as minus HFC by 1 plus HOC RL or RL2 into AI1 is minus HFC by 1 plus HOC RL1. These are the equations we got in case 1 and case 2 analysis. However, we know HOC is very small when compared with the value of 1. We can approximate the first term as just minus HFC. HOC is close to 0. Therefore, this HOC RL2, this term HOC RL2 is much less than 1. As a result, this first term can be approximated to minus HFC. Similarly, in the second term also, HOC into RL1 is much smaller than 1. Then we can approximate the second term also equal to minus HFC. That means we can approximate this value to, of course, minus HFC is nothing but 1 plus HFE. According to conversion, H parameter conversion equations, minus HFC is nothing but 1 plus HFE into 1 plus HFE. Since 1 is generally small when compared with HFE, we can approximate this equation to HFE into HFE. Or, of course, HFE is nothing but beta. This HFE is also nothing but beta. So, altogether, this is overall current gain is approximately equal to beta square in case of Darlington pair amplifier. Since overall current gain in Darlington pair amplifier is beta square or beta into beta, it is very familiar with the name beta multiplier. It is popular as beta multiplier. This is about overall current gain. Now, in a similar way, let's look into overall input resistance. Step 3 is overall input resistance. We know in any multi-stage amplifier, overall input resistance is simply equal to input resistance of the first stage. So that means Ri1 should be the overall input resistance, where we got a formula for this Ri1 as HIC plus HRC AI1 RL1 is the formula we got for this. Then we can write it as HIC plus, of course, HRC is equal to 1 according to H parameter conversion formula. Then you keep AI1 as it is. Then RL1 is nothing but Ri2. Output load resistance of first stage is nothing but input resistance of second stage. Load resistance of first stage is nothing but input resistance of second stage. So, we can rewrite this equation as HIC plus, of course, AI1, just now in the previous analysis, we have approximated this AI1 as 1 plus HFE into Ri2 is nothing but HIC plus AI2 RE. Ri2 value is HIC, of course, plus HRC into AI2 RE. But we know HRC equal to 1. Therefore, I removed HRC from that. Then AI2 RE I wrote. Then this equation becomes HIC according to H parameter conversion formula HIE plus 1 plus HFE into HIC, it becomes HIE plus AI2 can be approximated as 1 plus HFE. We did it in the previous case, in the previous step in fact, into RE. Then this becomes HIE plus 1 plus HFE into HIE plus 1 plus HFE square into RE. This is the overall input resistance in Darlington pair amplifier. If you carefully observe this formula for overall input resistance, we know typical value of HIE is around 1100 ohms, means 1.1 kilo ohm. 1 plus HFE, for example, if it is HFE value, if you take it as 100, 1 plus HFE is 101 into 1.1 kilo ohm plus 1 plus HFE square means 101 square into REE, just roughly if you take it as 10 kilo ohms. Just imagine with this just approximate values which I have selected, the overall input resistance is more than 1 mega ohm. That means the overall input resistance of Darlington pair amplifier is generally very high, generally in the range of few tens of mega ohms. That's why Darlington pair amplifier is popularly called as high input resistance amplifier. High input resistance amplifier. As the input resistance of Darlington pair amplifier is in the range of few tens of mega ohms, it is popular as high input resistance amplifier. Now, let's look into the output resistance finally. Again, the output resistance in a multi-stage amplifier is simply equal to output resistance of the last stage. In our Darlington pair amplifier, the total output resistance should be equal to output resistance of the second stage. That means R0 should be equal to R02. Then recalling the formula for R02 we got, this is 1 by HOC minus HFC into HRC by HIC. Of course, we obtain this equation in case 1 while analyzing second stage CC amplifier in Darlington pair amplifier. We got the equation for R02 as 1 by HOC minus HFC HRC by HIC. Then converting these values into common emitter using conversion formulae, this is 1 by HOC conversion formula is HOE minus HFC is 1 plus HFE, HRC is 1, HIC is HIE. According to conversion formulae, I have converted HOC, HFC, HRC and HIC into common emitter parameters. Then we know HOE is close to 0, very small when compared with 1 plus HFE by HIE value. As a result of that, this equation can be approximated to HIE by 1 plus HFE. This is the formula for output resistance, overall output resistance in Darlington pair amplifier. HIE is generally 1100 ohms by, even if you take the lowest possible value of HFE, means 50. So 1100 ohms by 51 if you consider. So 1 plus HFE becomes 51. Then the output resistance can be approximated to 21.56 ohms. Means very low. So the conclusion is output resistance in Darlington pair amplifier is very low. With this, After analyzing for overall voltage gain, overall current gain, overall input resistance and overall output resistance, we can have a summary like this. In Darlington pair amplifier, AV is approximately equal to 1, Ri is very high and R0 is very low. Based on these three characteristics of Darlington pair amplifier, one can easily come to a conclusion that since voltage gain is 1 or unity, very high input resistance and very low output resistance in Darlington pair amplifier, it can be used as voltage buffer in real-time electronic circuits, because unity voltage gain, infinite input resistance and zero output resistance are the qualities of an ideal voltage buffer, and the characteristics of Darlington pair amplifier are much close to the characteristics of an ideal voltage buffer, so that a Darlington pair amplifier can be used as a voltage buffer in real-time applications. The real-time or practical application of Darlington pair amplifier is voltage buffer. And it is also, because of its high input resistance, it can also be used as a high input resistance amplifier. And the current gain in case of Darlington pair amplifier is very high, and that too it is equal to beta into beta. Darlington pair amplifier is popular with the name beta multiplier. These are the specialities or special characteristics of Darlington pair amplifier as a multistage amplifier. So this is the procedure you need to follow to analyze any of the multistage amplifier, not only Darlington pair amplifier. Even if you go for CE cascade amplifier, CE cascade amplifier, CB cascode amplifier, in all those three amplifiers analysis also follow the same procedure and try to analyze them. Remember, steps to be followed. First, you analyze second stage in any multistage amplifier. Then in the second case, analyze the first stage. Then in the third case, consider the results you got in case 1 and case 2, means analysis of stage 1 and stage 2. You take those results into account and then finally estimate the overall performance of that multistage amplifier. Based on the overall performance in terms of voltage gain, current gain, input resistance and output resistance, decide the applications of that particular multistage amplifier. This is the procedure you need to follow in the analysis of any multistage amplifier. That's all.